Okay, organic chemistry 2341. We're going to continue with the second part of chapter 8, talking about addition reactions on alkenes and alkynes. So, our first uh, set covered the hydrohalogenation, what we learned was both syn and anti. Now we're going to learn about the syn and anti additions for hydration, or adding adding water across the double bond such that we can get alcohols and ethers. Okay, so the first thing we have is we want to do an electrophilic addition of water across the double bond. This is typically done with an acid catalyzed like sulfuric acid or phosphoric acid. And we have a Markovnikov rule applies, meaning the hydrogen is going to be on the more hydrogenated side and the alcohol is going to be on the more substituted side. Okay, now because we're going through the carbocation intermediate, we will have syn and anti addition, and therefore we can also have carbocation rearrangements occur. So if you had a secondary and it'd be more stable as a tertiary, you can get these reactions to go through that rearrangement. Okay, so if you replace water right here with an alcohol, what happens is the same mechanism applies. You get hydration of the, you have hydrogenation of the double bond generating the carbocation, and then you get attack of the carbocation by the alcohol yielding an ether here. So, but it's the same mechanism applies for both the ether and the hydrogenation. So let's take a look at that method of mechanism. So because it's acid catalyzed, the first step is the formation of the hydronium ion here. Then we have addition of the electrons from the double bond attack the hydrogen here, and then that liberates a free molecule of water and gives us our carbocation. Okay, now our carbocation is interacted with the electrons of the water to generate our new sigma bond to give us our protonated alcohol. Once we have our protonated alcohol, our water in the solution can act as a base and deprotonate our alcohol, liberating a free alcohol plus regenerating our acid catalyst from the beginning. Therefore, it's catalytic acid because we regenerate it at the end of the mechanism. Okay. So what if we want to run this reaction where we don't have a rearrangement, but we still get the Markovnikov addition? We have a reaction for that, and that's called oxymercuration, demercurization. In this case here, we use mercury right here to bond to the carbon and keep that carbocation from moving around. So what happens is we have addition of hydrogen to the most hydrogen substituted carbon, and we have the alcohol on the more carbon substituted carbon. Now, because of the way this works, we get a mixture of both syn and anti addition, just like we would in the carbocation, but because the mercury is sitting on top of that carbon, it doesn't allow that carbocation to move. So this is really good because we don't really need an acid, and that's a very high yielding reaction. However, it does use a toxic reagent of mercury acetate. Okay. Now, if you wanted to create that ether instead of the alcohol, you can do that. You just have to change the catalyst slightly. And what you'll end up with is the alkoxymercurization, demercurization, but you'll still get your ether on your more substituted carbon, and your hydrogen will be added to your terminal or less substituted carbon. Okay. So if that gives us a way to add things in a Markovnikov addition but doesn't allow for a cation rearrangement, let's find a reaction that gives us an anti-Markovnikov addition. So that the alcohol is being added to the least substituted side, and we're hydrogenating the more substituted side. And we have a reagent for that. It's called Hydroboration. And the reason it works is that when we add the borane reagent across the double bond, the boron goes on the least substituted carbon. And then when we oxidize that boron off, it gives us our alcohol on the least substituted carbon. Now, this works especially well when you have a big, bulky borane reagent, so it wants to be on the least substituted side. And we can have no possibility of rearrangement because it doesn't form a carbocation immediate. Okay. So the key here is that it forms anti-Markov because it gives us our alcohol on the least substituted side. So what does this mean for us? It means if we want a highly substituted or the most substituted alcohol, like a tertiary alcohol, we can go with this acid catalyzed addition of water. If we wanted to make sure we didn't get a rearrangement, we can use this oxymercuration, demercurization. And if we want the least substituted alcohol, we can use this borane. Okay, so how can we use this to our advantage? The way we use this to our advantage is we can use the same substrate and generate all three types of alcohol by choosing our reagent. So if we choose our acid catalyzed hydration here, we can form it initially the secondary carbocation, but because we can get cation rearrangements, we'll actually convert a significant amount of it to a tertiary alcohol because that carbocation did a 1,2 hydride shift. If we use the mercurization demercurization mechanism right here, the mercury will attach directly here, but it will not allow for a rearrangement. So we end up with our secondary alcohol. And our last reaction, of course, is this boration deboration reaction, where the boron will add to the terminal site and then give us our primary alcohol. So the same substrate here can generate a tertiary alcohol, a secondary alcohol, or a primary alcohol by choosing the correct reaction system.